I'll write the topic, you write with me. I like this part, okay? This thing that we are going to do now. Graphically, it's a long topic. Graphically illustrating the set of numbers within brackets, points, satisfied by a simple condition. Graphically illustrating the set of numbers satisfied by a simple condition involving complex numbers. Involving complex numbers. Graphically illustrating the set of numbers on the complex plane, that means points, satisfied by a simple condition. Now, this is a long topic, but this is something that you have done in O-levels. Again, I'm going to start from that prior work that you have done, and we will build on it so that you will see the connection between what you have done before and what we are going to do now. It's just the same things that you have done before with real numbers, we are going to be doing with complex numbers. So that's what we are doing, right? After after we discovered that, oh, people have created this thing long time ago. So we just learned it. And we are just familiarizing ourselves with working with complex numbers. So this is a long topic, but I don't know whether you understand from the topic what this is about. So let me start with an example. You will quickly remember, oh, we have done this like in grade 7, okay? So I'm going to start with, so this is recall. We will start from there and then we'll transition to the complex plane. We'll start with the real number line. Recall. So just a little recall. When we were working with only our real number line. Number 1. If I say illustrate, remember, see whether you remember this. If I say illustrate, I give you some condition on a real number. I say real number x is equal to, like, okay, is equal to 2. Can you illustrate this on the number line? Graphically. So diagram. How would you do that? You would draw the number line. Some 1, 2, 3, 4, -1. Very good. Happy remembers. Do you remember this? Like if I tell you, can you show me x equals 2 on the number line? Let's mark it in red. you can write here itself, just draw a little circle, shaded one, right on top of 2. X is equal to 2. I'm showing you where that number is on the line. So this is my condition. X equals 2. That's just one number, and it's right there on the number line. Some of you might do it like above the line. Let's do it right on the line, okay? So we are showing where that number is as a point. Oops. Is this clear? Can you do this? Illustrate. Number 2. Illustrate X. I think I will both these conditions. I'll write the condition in a different color just to highlight it. Here it was X is equal to 2. Can you do X is greater than 2? Can you illustrate that on the number line, on the real number line? Oops. You would draw your line. Some points. What I don't like with the Zoom whiteboard is, you know, little pieces of lines get drawn, like when I keep my hand, but it doesn't happen with the other one. Okay, how do I show this? X is greater than, very good, yes, correct, Happy. X is greater than 2. Can you show me all the real numbers that satisfy this condition? I have given you a condition. X represents a real number. Show me all the real numbers that are greater than 2. Illustrate it on this number line. You have done this in around grade 7, 8. So, greater than 2 can't be equal to 2. So you draw a circle, don't shade it. Greater, so greater means this side. This goes on. You can just draw an arrow to show, keeps going until infinity. All the numbers till infinity, starting from 2, but not including 2. So I have illustrated graphically in red all the numbers on the real number line that satisfy this condition. Okay. Can we go to number 3? Can I change the screen?
Okay.
Number 3. Illustrate X is less than or equal to 2 on the real number line. So, 0 somewhere, I have to show 2. Actually, 2 is what you need to show. So you can place it in the middle and have a few numbers to written to the right of 2 and to the left of 2. 2 can be in the middle in your diagram, like I haven't taken it like that. So how do I show this? All real numbers that are less than 2 can be equal to 2 as well. So you would start with 2 Can be 2 means you circle it. And then any of all these. Right? And go this way. Clear so far? These are things that you have done before. Here's the next. And we are step by step. We are looking at more complex conditions. Okay, here's number 4. Can you illustrate this? Mod of x is equal to 5. So I'm dropping the part on the real line. If I use x as the letter to represent that unknown number, then I want you to work in the context of real numbers. That's the indication. Okay. If I had used z, then you have to think of the whole plane and think of what are all the complex numbers that satisfy this condition. But right now, I'm only working with the real number line. So how do you show this? What are the numbers? What are all the numbers whose modulus is equal to 5? Set of numbers. Here you have an infinite, in this number 3 example, you have infinitely many real numbers that satisfy this condition. For this 4th one, I'll give you time to think and do it. I hope you remember the meaning of modulus of x. Hatfi, you are saying this to this too? If I write this in words, what modulus of x means in words, what this means in words, if I write, it's a symbol. What does that symbol mean in words? What's the meaning of that? Distance from 0 to x. That's the meaning of modulus of x means distance from 0 to x. Must be equal to 5. What number satisfy that condition? That's correct, Happy. So what are the numbers?
0 to 5.
What?
0 to 5. The range.
0 to 5.
It's the distance now between. That means so that's what it means, right, Miss?
Distance from 0 to 5, Nathan, must equal 5. What can x be? Any number from 0 to 5.
Wait, Miss. As long as the distance is 5, x can be any number. So, like, if let's say it's minus 1, it can come up -4. That way it can come no 5 distance.
Wait, are you saying? Let me draw it. I'm just drawing both sides. This goes on. What? Show me the numbers that satisfy this condition. Think, please. There is a simple thing I'm asking. Can you show me all the numbers on this line that are 5 units away from 0. Distance from 0 to this number must equal 5. Yes, Hakri, you are right now. Others? Okay, Malik, yes. Is that all? Let me know when you're done.
That's the answer, right? Just you don't draw a line, right? Because it's not a range.
How many numbers satisfy this condition?
Only 2.
Only 2 numbers. Nathan, and the way you have drawn it is wrong, Malik. If you leave us open circle, you're not showing anything. Open circle means not including that. I mean, there's nothing there.
Okay.
So it's the number 5, only the number 5 is 5 units away from 0. And also minus 5 is 5 away from 0. Nothing else is 5 away from 0. How can you, if you thought of like that, from is 1 5 units away from 0? Is 2 5 units away from 0?
No.
Is that clear, Nathan? I'm saying equal to 5. This distance from 0 to x must be 5. Then it's only 2 numbers in this set. I'm asking what set of numbers satisfy this condition? Illustrate it on the number line. Only 2 dots, 2 numbers, 2 points, 5 and minus 5, and that's all. Is that clear? I need a response. Is that clear, Nathan?
I'm still trying to wrap my head around it, but
Okay.
I think I'll be
Okay, I'll
able
give
to
you
understand.
time. I'll give you time to think about it.
No, now when we do versus, now we'll be using this for some examples now when we're doing questions. So then I'll be able to, like,
No, you have to understand this example.
Yeah, no, I don't understand this. No.
You don't understand, right? Okay. Nathan, what
Can you do
numbers?
another?
What?
Can you do another question, miss? Then I might.
Same thing. I mean, no point giving another. I can just change this 5 to another different number 2.
Okay.
Or 3 or something like that. Same thing. So let me explain this. What I'm asking is, what numbers are 5 units away from 0?
Wait. Can
Nathan?
units? Miss, can units also mean steps? Like how many
Unit
steps?
means 1 unit. Unit means this distance. This is 1. Yeah.
Yeah,
the unit means that.
It can also mean steps. No. Okay. If I thought it as steps, then yes. Then okay. No, because I take that from 0 to 1 is 1 step. 1 to 2 is the second step. That way. Now I understand. 5 units or 5 steps. Okay, away from 5. Okay. Understand.
Okay.
0 is the origin.
A unit means 1. Unit means 1, 1.
Yeah, I get it now.
So 5 units means 5 of those.
Yeah, understood.
Right. Okay.
Yeah.
Then number 5. I'll go to the next page. I'm going to drop the whole illustrate, I will just write the condition, okay? You know what you're supposed to do. Illustrate all the numbers that satisfy this given condition on the real number line. I should have given it on top. Here's my 5th condition. I'm just thinking whether I should recall. This is recall, it's okay. X minus 2. Modulus of x minus 2 is equal to 3. And for those of you who can't quite remember, let me write a tip, like a little tip for you on the meanings of this. This means if you have x minus some fixed number, x is a varying number, if I give you x minus some, like x minus 2 or x minus 5, okay, that means this is fixed number. Means, what does this mean? Can you remember? If you have x minus a, where a is some fixed number, that means distance. Let me see whether you're saying it. Are you saying it? What, something is going on here? No. Distance from a to x. Means distance between a and x. Shall I say distance between a and x? Let me say put between, that distance between a and x. So that means what I have, if I translate this into words, what I'm saying is distance between, show me all the numbers x, so that distance between x and 2 must equal 3. Can you show me all such numbers on the number line? First find 2. Here's 2. Here's 2, right? Which number or numbers are 3 away from 2? 3 away from 2. The distance between 2 and my number must be 3. Good, Hatvi. Is that all? That's correct. Can someone else? Very good, Netni. Yes, that is correct. Can someone else also tell me? Umalya says 2 to 5. No, you're again mixing this up. Okay, so Umalia says 2 to 5 and minus 1 to 2. So basically now if I show that below this like that, no, Umalia, you're saying all the numbers here from 5 to minus 1. Is that right? Okay. So for example, according to your illustration, number 3 also satisfies this, right? Is this number 3 units away from 2? My number x must be 3 units away from 2.
Excuse me, miss.
Yes, Malit.
Is my answer correct? I just do it on the...
Correct. Do you understand this? This is like, wait, I mean, if I give a different analogy or a little story for this, I don't know, this concept is very simple. It's like this. Now, you have this road. This is your real number line. You have this road. When I say x minus some fixed number here is equal to some number here, you think this fixed number is like a tree on the, it's like a tree on this road. And this is you. This is a tree. Why am I taking a tree? A tree is fixed. It won't walk here and there. It's a fixed position, fixed point on the road, right? If I say, can you go and stand so that the distance between you and the tree is 5? Where can you stand? This is just a line, one-dimensional thing. Where could you go and stand? How many positions are there so that the distance from the tree to you are the variable. You can go anywhere. Your location can be changed. You're a variable. What are the positions you can be in so that the distance from the tree to you is 5 units? Do you understand? You can be 5 away onto this side of the tree. Sorry, 5 away here. This is you. You can go and stand here, or you can go and stand here. Isn't it? Think like that. So let me bring that whole. I think that's a good analogy. Think of this as always when you have something like this. This is a tree. This is a tree. This is you. And this is the distance from the tree to you. You go and plant this tree. So this is at 2. The tree is here. So you can be here. This, Malit, what Malit had put was right. You can be here or you can be here. This dot I have to remove, but when I try to remove it, the whole thing might go. Yes. So sorry about that. Is that clear? So Malia got it understood. Everyone else, is this clear? This 2 is the point 2. It's a fixed place now. It's a fixed place. From that fixed point on the number line, where can you be if the distance between that fixed point and you is 3? So just 2 points. Okay, number 6. Here's the condition. X minus 2. So this is you. You have the distance between you and a tree that is planted at 2. Position 2, point 2, okay? The distance between you and the tree must be less than 3 units. Where could you be? Show me all the possible points that you can go and stand on the number line. So first mark the tree. Here's the tree, right at 2. Mark it in the middle. From 2, I have to think of all the numbers that are less than 3 units away. Less than 3 steps away from 2. That's correct. So I've drawn the 2 a little big, okay? That's my fixed point. Now where can X be? Yes, Netne. Do others get this? Shall I show you?
Miss,
Yes.
is it more versus less than -1 and greater than 5? I mean, the zeros and values, they go from more greater than 3, right, Miss? This is no less than 3. Less than 3. No. It's less than 5 and less than -1. That means not including
greater than -1. Less than 5 and greater than -1.
Yeah. Greater than -1. Yeah.
Yes. This
not
shaded. Not shaded. Anything in between could work. You can be on top of the tree. You can be here as well. On 2. You can be 2 itself. Then distance from 2 to 2 is 0. And that is less than 3. So you can be there as well. And you can be anywhere here. I mean, even in this diagram, I can show you that from 2, you're 3 away. Yeah, that's why you can be here or here. In this, your distance from the fixed number 2 to you, your varying number should be less than 3. So you can be anywhere between -1 and 5. Okay. Okay. Next example. Still, these are recall, and we are still on just the real number line. Number 7, I think now. Here's the condition. X plus 1, plus, not minus, is greater than or equal to 2. Now we can't give a meaning to X plus a number. We have a meaning for X minus a number, means the distance between X and that number. So if you have X plus a number, you have to rewrite it. This is the same as saying X minus what number? X minus what number? So you turn it into X minus 1. Very good, Nathan. So now it's the same thing. The distance from X to -1 must be greater than, can be greater than or equal to 2. So I will start with the fixed tree in the middle. -1. The number, fixed number is -1. It's like at that point. Then from that point, you have to be 2 steps away or greater than that. 2 steps away or greater than that. Greater than or equal to. I hope this is clear now. Yes. No, Hathi. Would someone like to annotate on the screen and do it? Show me. Quadratics? What are you talking about, Hathi? You are going to, okay. You are talking about solving this algebraically. You don't, yeah, I mean, there's nothing to solve. You can solve without thinking about anything. You can very mechanically solve this and get what range of numbers you get. You can do that. But you don't need to solve this. If you think about the meaning, you can figure out the solution. But yes, that's a possibility. You can do that. If you want to solve this, you will square it and you will get a quadratic and you have to do the parabola thing, and you don't have to go into all that. No, it's not 3 and minus 1. This is an inequality. You get a range of numbers. So Maliti is right. All numbers from 1 beyond and minus 3 below. Okay, yeah. Okay, because you have to be, this is where your tree is. You have to be 2 units, or so you can be here or anywhere here. Put an arrow to show it goes. You can be here or anywhere there, because you have to be 2 steps away from the tree or more than that. Is this clear? Okay, now. Are we ready to move on to the complex plane? And I will give similar conditions. So if you look at all my conditions, they were either a little equality, an equation, or an inequality. Look at all my examples. Here, this was an equality. My condition was an equality. Here, my condition is an inequality. Okay, so with the use of either an equality or an inequality, I can set a condition and ask you to show me all the numbers that satisfy this condition. We practiced up to the 7th example, just the real numbers. Okay, now let's look at similar examples with complex numbers. So you write like a little sentence. Now let's look at some similar examples. On the complex plane. And remember, whenever I say the complex plane, it's the Argand diagram. I don't think I gave you that name anywhere in my notes. I don't like that word. I avoid it. But I want you to know, I call complex plane what you call the Argand diagram. Argand diagram? When you say Argand diagram, it's a diagram. No? This is the complex plane. So just remember that in your exam questions, they might say Argand diagram. You replace that with complex plane. That's the same thing. Now let's look at some similar examples on the complex plane. Not just the real line, the whole of the plane, the complex plane. Now you can come up with conditions. Like for example, show me all the numbers whose what? You can say whose real part is equal to this much, or show me all the numbers whose imaginary part is equal to this much, or show me all the numbers whose modulus is this much, or show me all the numbers whose argument is this much, isn't it? Like, remember, think of the features of a complex number. Now, then you can put a condition on one of those things. You know, real part is this much, imaginary part is this much, or the argument is this much, R is modulus is this much, and you can show all the complex numbers that satisfy that condition. Okay, so I'm continuing the numberings. It's number 8, and here's my condition. So the question goes, illustrate all. Let me write it just for this. Illustrate all complex numbers that satisfy this condition. The condition I give in, oh, I think I messed up the colors. Here's the condition. Re of Z, I want re of Z to be 2. Real part is 2. Illustrate all complex numbers that, shall I say whose? Does that make more sense without saying that satisfy? Shall I say whose real part is 2 on the complex plane? Illustrate on the complex plane. That's how the whole question might look like. Illustrate all complex numbers, and here's the condition, whose real part is equal to 2 on the complex plane. Can you show me on the complex plane all the dots, all the points on the plane? Remember, any point on the complex plane represents a complex number. So you are showing the graphically as a point. Show me all the points who satisfy this condition. So you now have to draw the whole grid. Here's the complex plane now. Don't forget to label your axes. I'll mark a few. I think I would need 2 to be on this, so that's not a problem. Then I have I, 2i, and so on, minus I, and so on. You give it a try. If you were to show with dots all the points whose real part is 2, show me, like, it could be a whole region of numbers now. Like, you might have to shade a whole region, or it could be like a line, like earlier, or it could be just one number, like just a dot, or like 2 dots. I don't know. I'll let you think about it and do it. If someone wants, you can annotate. Yes, Tarindu correct. Hatfi is correct. Any number on this line passing through 2, for all those numbers, including 2, purely real number 2, the real part will be 2, isn't it? Those are different numbers, but all their real parts would be 2. It would be 2 plus I, 2 plus 2I, 2 plus some I, 2 plus some I, 2 plus 2 minus some I, 2 minus some I. I mean, 2 is fixed if you think of all the points passing through 2, vertical line. Okay, so Hatfi is correct. Let me draw it like a little bit nicer. So it's a line passing through 2, like that, all these numbers, and you put 2 arrows to say that it's a vertical, like a long line, right? Infinitely long line. Is that clear? All the points on this line, for all the numbers on this line, the real part is 2. So I have shown all the numbers who satisfy this given condition. Is this clear? Is this clear?
Yes.
Yes. Okay. You ready for number 8? Okay.
Number 9.
Sorry, number 9. Number 9. Can I just give you the condition without writing the whole thing? So you could have put that on top, common to all these questions. Illustrate the all the numbers satisfying the given condition on a complex plane. Okay, that's the question, and I will just write the condition. This time, can you show me all the complex numbers whose imaginary part is equal to -3? Can I copy this whole thing and bring? I think I should be able to do that. Select. Right. No, can I copy this? No, I can't. So it's no point.
Miss, imaginary part is equal to -3.
-3.
Miss, can you go to the previous slide for a second? Okay, Miss.
Yes, Tarindu, it's similar to an XY coordinate plane. Yes. Not their name. This is a complex plane where your numbers are. But of course, there is a huge similarity between this and, I mean, when you think of for example, when you think of a number like this number over here is 2 plus I, the coordinates there are 2, 1 if it is a coordinate plane. So these two are actually it's like, this is the real part, this is the imaginary part. I mean, there is a similarity. Conceptually, they are different things. But huge, yes, very similar, and you can switch between the two worlds and something that you are thinking about a coordinate plane. would apply to this. Yeah, it's very interesting. Won't we have to bring in the... What? Yeah, what are you saying? I forgot the zero here. What if we have to bring in the complex plane and y-axis together? What do you mean by that? Now who's drawing this?
Me. You're wrong.
Oh, that is wrong. You have shown.
Okay, fine.
No, I mean, okay, fine is not, should not be your answer. You have to think, why is it wrong? Let me see. But what are the numbers I have represented?
Oh, no.
You drew, were you trying to draw a line through 3 on the real axis?
No, I remember my mistake. That was wrong. No.
Huh?
Nah.
I
wrong.
didn't understand what you said.
It's wrong. What I did was wrong. Totally wrong.
Can you retry?
Yeah. Okay.
Because, what if we had to bring in the x and y axis over? Okay, no. I will talk about this, okay? What do you mean by you had to bring in the complex plane and the y-axis together? The thing is this. I hope it's okay if I talk about this now. Don't get confused. In your xy coordinate plane, the xy coordinate plane was formed when you only knew the real number line. When the only type of numbers you knew about were the whole number world was only the real number line. You place one real number line this way, you place another real number line vertically to it, and you formed this plane like a reference, a pair of axes that could be used as a reference to give the location for other points in space. It's a reference frame. Coordinate plane is a reference frame. What does that mean? Now you think you go to outer space. Say you are in outer space now. You are in empty space. There is nothing around you. It's all empty, just space. So you are just floating here and another person is floating there. There is no way in which you can sit down. Say you are just floating here. You don't know how to say where you are. You look around, there is nothing. Where are you? You wouldn't know where you are. You can only give a location of something relative to another thing. You can say, I am in front of Pereira and Sons. That's how you say, right? Where are you? I'm near the gate. Like if you were just standing or like floating in empty space, how would you say where you are, your location? You need a reference. I'm under this tree. Because you give your location relative to a fixed thing that is in the space. So this coordinate system is used as a reference. Now, for example, if you want now, this is a whole different thing I'm talking about. I'm diverting from this question. I'm just answering one of your, Hatfi, and you haven't put it to everyone. Can you put that to everyone? I'm answering Hatfi's question. Like the use of a coordinate plane, XY coordinate plane is this. When you want to talk about a map of something, say Sri Lanka, or even say you have a cricket ground. You have a cricket ground, right? In order for you to be able to like talk about things easily, you place in your mind, you imagine that you have a coordinate plane. You place it, that's a nice way to place it so that there is a symmetry. Right? To impose this on top of this picture. This is a cricket ground. So there is a player here, there is a pitch here, there is another player here. Now you can say where this player is using this coordinate system. You can give it a location. This one is at -2, 4, 5, something. Now the ball is going like that. The ball is going in the line y equals 3x plus 2. You see, like, you can talk about things. All these become possible because of the placement of this coordinate plane. That's the use of it. It gives you a reference. It allows you to talk about things relative to these axes. But the problem is, like, x-axis is a real number line. Y-axis is a real number line. Now we know that lines can be on a plane. So if you are to create a coordinate system, your x must be a whole plane and your y must be a whole plane, like 2 planes, if you want to put all the numbers into consideration. I will just throw it out there for you to ponder. I was answering Hatvi's question. So a complete coordinate system would be not just the placement of 2 lines, it must be the placement of 2 planes, because your numbers are a whole plane. This we used. I don't know whether what I'm saying makes sense to you. If it doesn't, just forget it. Shall we go back to this now? Okay. How do you illustrate this? Find one number whose imaginary part is -3. Can you write an example here in this box? Can someone write one example for a number whose imaginary part is -3? Nathan, because you got it wrong. Can you give me one example? Just tell me a number whose imaginary part is -3. Give me an example.
With -3, no, miss?
Nathan?
Its imaginary part is -3.
Imaginary part is -3.
Okay,
Can you give me an example for such a number?
Is it the whole real number line?
Can you just give me one example?
Okay, fine. 1. That's it.
Give me a number
Yeah.
whose imaginary part is -3. Who has -3 of imaginary part?
Is it?
Didn't hear.
Is it 0?
Say it again.
0.
0. Okay. Now you think this is an example for a number who has -3 imaginary part.
Okay.
Now forget everything. Now just think of the number 0.
Okay.
What's the real part of number 0? What's the imaginary part of number 0?
The real part? Wait.
Any complex number Nathan has
Yes.
a real part and an imaginary part. Do you remember that?
Yes. They have both. Yeah, they have an imaginary part and real part.
Any
Yes.
complex number,
Yeah.
I will say it again. Any complex number, any complex number, meaning any point on this plane. 0 is a point on this plane, so 0 is also a complex number. So any complex number has a real part and an imaginary part.
Yeah.
So number 0, what's the real part of number 0?
0.
What's the very good. What's the imaginary part of number 0?
0.
Huh?
That was a 0.
But then you gave, that's correct. But then you gave this as an example for a number whose imaginary part is -3.
That is -3.
What?
No.
Can you rethink? Calm
Okay,
down,
hold on.
Nathan. Can you rethink?
Okay.
Can you take
-3.
your time and rethink? Can you take your time and rethink of a number? Any number, there are infinitely of them. Can you give me one number whose imaginary part is -3?
Okay, so that is imaginary number is -3. Which
Imaginary
means
part,
in other terms,
-3. Imaginary
that
part.
is bi. So what is a? A is
Okay.
yeah. I can give the example as like -3. No, so that could be. I can take 1 as an example, or I can take 0 is the example.
We just discussed that 0 is not an example.
Okay, fine. Sorry.
Wait,
Can you
why
give
are you saying
one?
that again? Are you not convinced? You said that the imaginary part of 0 is 0.
Yeah.
I am asking for a number whose imaginary part is -3. Okay, so there are 9 of you here. Each person, I want you to give me, either write it in the chat box or say it to me. I'll start from top. Nathan is on top. So I'll come to Nathan in the end. No, I'll start from the bottom. Umalya, give me an example for a complex number whose imaginary part is -3. I'll write each of your examples here. Umalya. You are not Umalya, but I'll take your example. Tarindu is giving 1 - 3i. Very good, Tarindu. The number 1 - 3i has a real part of 1 and an imaginary part of -3. Umalya, can you give me another example? Malit is giving 20 - 3i. Very good. The real part of this number is 20. The imaginary part is -3. Umalya. Rachel, somebody. Yo. Mihil, Joanne. Good, Nethni. Nethni is giving the example 5 - 3i. Very good. The real part of this number is 5. The imaginary part is -3. Thank you, Umalya. Umalya is giving 18 - 3i. The real part of this number is 18 and the imaginary part is
Excuse me, miss.
Katri is giving again -100 - 3i. Very nice. That's
Excuse
different.
me, miss.
Yes, Malit.
Miss, can I undate the answer on the board? Just
What answer?
the answer for this, the question you're doing right now.
No, don't do it. I
Okay.
want, I'm trying to like Nathan to get it. Joanne says 2 - 3i. Yes, these are all examples. That's correct, Nathan. Rachel is giving another one, 8 - 3i. I mean, how many such examples can you give? Infinitely many. What's the condition? No condition on the real part. It can be any number. Imaginary part must be -3. So you write a complex number in the form a plus bi. I am saying this b must equal -3. Nathan, what is so hard in that? Tell me. It's not that it's hard. It's just that you have forgotten what we did 2 weeks back. Or you haven't properly understood. So all these are correct. So I wanted to show all such possible numbers on this complex plane. So do you see that? And the thing, Nathan, what happened to you was you didn't know what real part or imaginary part meant. If you knew that, you would be able to give an example. Please revise the first day, second day, last week work. So it's like, okay, if I take you to the similar situation on a XY coordinate system, it's like if I ask you, can you show me all the points with a Y coordinate -3 on this XY plane? Nathan, can you do that? Can you show me all the points that satisfy this condition? Their Y coordinate must be -3. It's the same thing I'm asking. The Y coordinate is like, this is like the Y axis. No, this is the imaginary axis. Imaginary part has to be -3, right here, -3. So any number just -3i would be okay. Or any number like on this line, it's a horizontal line passing through -3i. Think of any number on this, a number here would be 1 -3i. The number here, 2 -3i. The number here, 3 -3i. Or in between, 2.5 -3i. On this side, a number here, -1 -3i. Nathan, is this clear? Is Nathan here? Has he left? Ah, you're here. Is this clear?
Okay.
Nathan?
Okay.
Okay. No, you have, were these examples clear to you? No.
Okay. This is okay.
So you need to revise, you need to rewatch. No, let me tell you. Please.
No, miss, it's just that complex numbers is a very hard chapter for me, but
That's why, okay, if it is a hard chapter, I want you to rewatch last time's video. Last time's recording, I will send it to you. I want you to rewatch, especially the first part. We learned this part. Hafi or Malita, somebody, can you give me that topic where we did real, imaginary, modulus, R, argument, all that's the set of, what was the topic of that note?
Some terminology.
Some terminology, the terms related to complex numbers. What do you mean by the real part of a complex number? What do you mean by the imaginary part of a complex number? What do you mean by the modulus of a complex number? What do you mean by argument of a complex number? These are terminology, terms, real part, imaginary part, modulus, argument. What do these words mean? We did this last week. So you were not able to do this because you have not either understood that or you have forgotten. So I want you to rewatch that recording. Okay, I will send you. So others, is it clear that it is a horizontal line passing through the -3i? For any point on that line, imaginary part is -3i. Right? Okay.
So they're just basically asking for what real numbers can they
what complex numbers?
Yeah. What
complex numbers
can
has an imaginary part of -3?
Yeah, -3. So then you can just put any number to -3, -3i. Like
showing all the points. When you show all the points, what you get is a line. Like if you keep plotting all the points, you show this number, this number, this number. If you keep showing everything, you'll end up with a line, and this is this line. Or the numbers, all the numbers on this line have an imaginary part of -3. This is a visual illustration of a set of numbers satisfying a given condition, right? This is the condition. These are all the numbers that satisfy this condition. What is the condition? Their imaginary part must be -3. Please write that there. just to emphasize. Are you ready to go to number 10? Are we ready to go to number 10, the next example? Yes. So now, okay, I'm doing one example from each type, okay? So number 8, I showed you a condition on the real part. Number 9, a condition on the imaginary part. Next, I will show you a condition on the modulus. Next, a condition on the argument. For different properties of a complex number, I can impose a condition. I want the argument of a complex number to be this much. Show me all such numbers. Okay, this is what we are doing. I hope it's clear to you.
Yeah, makes sense so far.
Sense now? Now number 10. Shall I write the whole sentence? Do you forget what we are doing after a little while? Because I don't write the whole sentence. Illustrate all the numbers that satisfy this condition. Now show me all z's whose modulus is equal to 3. If you want, you can go back and look at a similar example that we did on the real line. I will write the whole question. I think when I not write it, you lose the meaning. Illustrate. Or illustrate on a complex plane. And let me give you, like, just for once, the word Argand diagram. Illustrate on an Argand diagram. Argand diagram. That's just another word for complex plane. Illustrate on it would be a complex plane, or on the complex plane, all the numbers that satisfy the condition. What is the condition? I want the modulus. Z represents the complex number, a varying complex number, equals to 3. It's like asking, if there are a group of people, I ask you, show me all the people whose height is 4 feet, no, 3 feet. What's the average? 3 feet should be okay, I think. No, 4 feet, 5 feet, right? 6 foot is tall, very tall. Like saying that I give a condition. I pick a certain feature of people and put a condition. It should, height must be this much. Go show me everybody who has this height. Or show me all the people. Show me all the people in a group of people whose age is this much. You know, it's just like that. When you take a complex number, it has certain features. It has a real part. It has an imaginary part. It's like when you take a person, he has a height, he has a mass, he has a skin color, he has an eye color, hair length, I don't know. Like you, and then you can say, show me all the people who has brown hair. You put a condition on the hair color and ask you to show all the people who has that condition. Just like that. So here on the complex plane, there are numbers sitting on the complex plane. Any number has a real, what is called a real part, an imaginary part, a modulus. A modulus means how far that number is from zero, the distance from zero. So it should be very clear what number, who should come for this. All the numbers who are 3 steps. Nathan, you can try this. Who are 3 steps from zero. All the points who are 3 steps from zero. Yes, Nethni, very good.
Miss, can I?
You want to, what, you want to annotate and do
I
it
think,
or like say it?
yeah,
Don't
yeah,
say it. Don't say it. If you want to say it, send a message privately to me.
no, I was gonna say annotate.
Before you annotate, let us
I think I
let
can
other people to try.
understand.
You understand, right? Yeah. 0. Say you have 1, 2, 3, 4, -1, -2, -3, -4, I, 2i, 3i, 4i, -i, -2i, -3i. Hi, Putu. First, find a few such numbers who's 3 steps away from 0. It's like, now here's an analogy. You have your tree. Now this is on a plane, like you can stand on at any point on a plane. It's not just on a line. So you have this tree at that point. If I ask you to go and stand 3 meters away from the tree, where can you go and stand? There is a tree on the ground. You have to go and stand. What are all possible places you can go and stand so that you are 3 meters away from the tree? What do you get? It's like your locus. What is your locus? So I can go and stand, say here, that if that is 3, I can be like here, if that is 3. I can be here, if that is 3. I can be here, if that is 3. I can be here. Like I have to be 3 away from the tree. Like that here, the tree is at 0. This means distance from, again I'm writing, I gave you this before. This means distance from Z to 0. 0, your tree, the fixed point is 0. Okay, Hatfi is saying, you can be here. You can be here. You will be 3 steps away. You can be here. You can be, is that all? Is that all? So 4 positions. Are there only 4 numbers whose modulus is 3? Whose size is 3? You draw.
There are infinite.
There are infinitely many. Okay, I will let Malith now to annotate. Netli gave the right answer.
You want me to annotate it, miss?
Yeah.
Okay.
Yeah, we get it. We get it. It's a whole circle.
It's not exactly accurate.
I know. Because anywhere on a circle, I will, Malith, I will just remove your, just so that I can redraw it, okay? Can I do it nicely? So, I mean, I can't do it properly because it's supposed to be a circle. Mine looks like an oval. It has to pass through these 4 points. It's a circle, okay? It's supposed to be a circle of radius. How much?
3.
Radius is 3. Center is at the origin at 0. Okay, so if I just write it, if I explain it in words, it is a circle of radius 3 units and center at 0, 0. I mean, let's say just 0. Okay. When I say 0, 0, it looks like a coordinate center at 0. Is this clear?
Yes, miss.
Okay. I'm going to stop.
I have a small problem.
What? No problem.
Uh,
You're starting to?
and it's a little bit confusing.
It's a little bit
If we
confusing.
draw a line,
What?
not this, I thought of something else. I thought of something else.
Huh?
It's a little bit confusing.
Okay. What is the something else?
Like if we take
Huh?
the numbers that have the real part equal to 3,
No.
then we have a vertical line from a vertical line that extends to infinity.
All right. Okay. Yeah. Yes.
So miss, if we take the magnitude of these complex numbers, as the I becomes more positive, then the angle, the argand of it will like continuously increase, but it will,
I lost you.
like
Say it again.
we draw a vertical line at x equals 3.
Okay, what is that? What does that represent? That
Any complex number which has the real part of 3.
Very good. Yeah. Okay.
And
That
we
we
extend
did.
it to infinity.
Yes, we did that example.
So then, if we try to find the magnitude of the complex number, it is the distance from 0 to the complex
Number?
to the point.
Yes.
Yeah. So as the I value increases to infinity,
Yeah.
then the angle in between
The angle increases. Angle
line
increases.
drawn and the x-axis will also.
Yes, the argument increases.
Like,
yes.
And it's confusing whether it reaches 90 or not. Does it reach 90 degrees or not?
Last sentence again?
Like, does the angle in between the line and the x-axis reach 90 degrees?
Okay. It approaches 90 degrees. Yes. You can say it approaches 90 degrees.
But it's never equal.
No. It is equal to 90 degrees only for points on the imaginary axis.
Oh, okay, miss.
Okay. So that what Tarindu asked has nothing to do with this example. I thought you were asking about this. Okay, I'm going to stop right here.